All right, today we're putting on our detective hats, our cosmic detective hats. We're going to look at how these tiny, microscopic specks of dust, and I mean tiny, found right here on Earth, can tell us the story of stars that died billions of years before our sun was even a thing. So, how do we even start? I mean, it sounds kind of impossible, doesn't it? How can a little speck of dust tell you anything about a star that died billions of years ago? Well, that's the big question we're digging into. Think of it like cosmic forensics, where your clue is smaller than a grain of sand, but your crime scene is, a whole star system. Okay, so our key piece of evidence, it's called a presolar grain. And the name really says it all, presolar. These are literal specks of stardust. They were made in the atmospheres of really old stars, wandered through space for, well, forever, and then got caught up in the big cloud of stuff that eventually became our solar system. So you can think of each one of these grains as a perfect little time capsule. It's like a message in a bottle, but it's from a star that died a long, long time ago. We're often talking about stars called asymptotic giant branch stars, or AGB stars for short. These are basically old dying stars that are puffing their outer layers out into space. And these little grains traveled all the way across the galaxy to end up here, carrying pristine info about what it was like inside that star. Okay, so if we're going to solve this mystery, we've got to examine the clue, right? We need to look inside, see what makes it tick, and our main piece of evidence here is a very special type of presolar grain. They call it a carbon onion. And no, this is not something you're going to find in your soup. These carbon onions, which we find in meteorites, like the famous Murchison meteorite, are these perfect little microscopic spears made of carbon. But here's the cool part. They're not just a solid ball. They have this really specific two-part structure, and that's where all the secrets are hiding. So let's break this down. You've got a core and you've got a rim. The outside part, the rim, is made of layered graphite. The easiest way to think about this is like the lead in your pencil. It's made of layers that can just slide apart. But the core? The core is the magic. It's made of unlayered graphene sheets. This makes the core super strong, super dense, basically a perfectly sealed little box. The rim is like a stack of loose papers, but the core is a locked safe. And that difference, that's the key to this whole thing. All right, so we know what our clue looks like. Now it's time to open our first case file. Let's use this little carbon onion to figure out what was happening in the final moments of its parent star. This is where the real detective work kicks in. And you're probably thinking, okay, hold on. How do you get from a tiny ball of carbon to, like, the temperature and pressure inside a star from billions of years ago? And that's a great question. The answer is you have to work backwards. You have to reverse engineer how it was made. Scientists have figured out it's basically a three-step process. So, picture this. In the atmosphere of this cooling star, you've got hot carbon gas. First, that gas condenses into tiny liquid droplets. Step 2, as things cool down even more, those little liquid drops solidify really fast, and bam, that's your dense, unlayered core. And for the final step, any leftover carbon gas just kind of sticks to the outside of that core, building up the layered graphite rim. And here's the thing. Every single part of this structure is a clue. The size of the core compared to the rim, that tells you how fast the carbon was building up. The density of the core, that gives you clues about how quickly the star was cooling. You can even look at other atoms trapped inside to get a chemical fingerprint of that specific star. It's incredible. And to read all these clues, scientists have this amazing nanoscale forensic toolkit. They're using things like electron diffraction to map out the structure, and something called HADF imaging, which lets them spot individual heavy atoms inside the grain. They've even got a tool called nanosims to measure isotopes, which is basically the star's unique DNA. So when you put all that data together, these cosmic detectives can build this amazingly detailed profile of the star. They can figure out its temperature, what it was made of, and even how fast its atmosphere was cooling right at the moment it pushed this little speck of dust out into space. A whole history from one single tiny clue. But wait, the story doesn't just end there back in the ancient past. In this really cool twist, it turns out that studying these old stars is helping us solve a totally modern problem right here on Earth: how to build the next generation of supermaterials. Yeah, it turns out that special structure in the core of the carbon onion, that perfect, unlayered graphene, that's something materials scientists have been desperately trying to make in the lab for years. And it seems like nature already perfected the recipe. It just did it inside a dying star billions of years ago. So what would we use it for? Well, the main goal is to create something called a diffusion barrier. That's just a fancy term for a material that's really good at stopping atoms from getting through. Think about helium, for example. We don't have an infinite supply of it, and its atoms are so tiny they can leak out of almost any container. We need something better to hold it in. And that's the big prize here. The researchers are aiming for, and I'm quoting here, synthesis of diffusion barriers with unprecedented capability. We're talking about a material so good at containing things, it could totally change the game for everything from storing fuel to building next-level electronics. So what makes this Stardust core so special? Well, remember how we said normal graphite is like a stack of loose papers? Those gaps between the layers are like tiny little highways for atoms like helium to escape. But the unlayered graphene in the Stardust core, it doesn't have those gaps. It's a merely perfect, seamless wall at the atomic level. Which brings us to the obvious question, right? If this stuff is so amazing, why don't we just, make it in a lab? It's a great question. The problem isn't knowing what to make, it's knowing how. And the reason why is, well, it's kind of mind-blowing. 7 orders of magnitude. What does that mean? It means 10 million. The way we cool carbon down in a lab is 10 million times faster than how it happens naturally in the atmosphere of one of these stars. Our methods are just too fast, too violent. The atoms don't have time to settle into that perfect, unlayered structure. They get rushed. So you see the problem. We can't copy the recipe until we actually understand the recipe. And these little Presolar grains are our only physical examples of it being done perfectly. We have to study these ancient time capsules to figure out how to copy a star right here on Earth. Okay, that brings us to the final chapter of our investigation. What's next on the agenda? Where do our cosmic detectives go from here to unlock not just the secrets of the stars, but the future of materials too? Well, the game plan is actually pretty clear. Step 1, get more clues. That means they have to keep painstakingly looking through meteorites to find more of these special carbon onions. Step 2 is to build better models, using the data from the real grains to fine-tune computer simulations. And finally, once they have that knowledge, they can start trying to invent new lab techniques that can actually mimic that super slow cooling process of a star. And really, this is the big takeaway from all of this. It's just amazing. The key to solving a huge modern engineering problem, making a material we've only dreamed of, it might have literally fallen out of the sky. It was just hiding in some rocks, waiting for us to piece the clues together. The ancient past is showing us the path to the future. And that leaves me with one last thought that's just so cool to think about. If the entire life story of a star and the blueprint for a futuristic material can be packed into a single speck of dust, just imagine what other cosmic secrets, what other world-changing technologies are just sitting there, waiting in the rocks, right under our feet. The search is definitely on.